So what made DeepSeek R1 and the new breed of language models so fast and therefore so cheap all of a sudden? Some of that is due to new training approaches for sure, but most of it is due to a whole new class of AI models, and we're going to cover both advances right now. As background, we posted a video on how language models are traditionally trained. See the link in the description section. But we will quickly recap in this slide. Starting with an untrained model that has useless random weights, we apply supervised learning using a wide set of language examples to get a trained model. This pre-training phase results in a decently trained model, but it still hallucinates too much and may produce responses that humans can find unsavory. So next, we align the model with human expectations by first doing a supervised fine-tuning step that uses input and response pairs pertaining to specific tasks like reasoning, knowledge, or creative writing. This fine-tuning phase gives us a model that is better suited to the task, but has only learned what we taught it explicitly in the training dataset. The real magic happens in the final reinforcement learning phase, where the model learns approaches that have not been explicitly described by us in the training dataset. And the very first big advancement that DeepSeek made was to improve the speed of the RL phase. 8 months before they released DeepSeek R1, they published a paper in April 2024 that described a variation on the RL algorithm that used way fewer computations, and therefore much less time to align a small model that solves math problems. It was a smallish model, only 7 billion parameters, but it validated their approach for reducing the training time. If you read their paper, there is a diagram there showing the absolute gory insides of a normal reinforcement learning algorithm on top, and how they simplified it in the bottom frame by removing the computationally intensive value model block. They call this approach the Group Relative Policy Optimization Approach, or GPRO for short. And that approach seems to be one of many tricks they use to train DeepSeek R1 quickly and therefore cheaply. And they showed off how quickly LLMs can be aligned with DRPO in their now very famous paper of January 25 that described DeepSeek R1. By the way, the R in the name of the model stands for reasoning tasks, such as writing software code, doing math problems, or solving word puzzles. They first pre-trained a large model that they call DeepSeek v3 to be a decent general-purpose LLM model, and then, instead of proceeding with the fine-tuning phase and then RL phase, they just skipped over the fine-tuning phase and went directly to the RL phase. Now, in about 2 minutes, we're going to discover that the secret of their speed is actually that pre-trained DeepSeek v3 model, so do not forget about it. Now, if DRPO was so efficient and fast, then they would be able to iterate quickly and discover, using reinforcement learning, new ways to solve reasoning problems without having to first prime the model with detailed questions and sample responses in the fine-tuning phase. And as the RL algorithm slowly updated the DeepSeek v3 model weights to be better suited for reasoning, the resulting updated model was called DeepSeek R10, where the 0 stands for zero fine-tuning. So, did this trick align the model to human preferences without a pre-training phase? Indeed it did, as this graph of theirs demonstrates. The x-axis is the number of times that the RL algorithm ran, which is a proxy for time, and the y-axis is the accuracy of the answers to reasoning questions. The dotted lines are the accuracy of the OpenAI O1 model, scored for 2 different accuracy criteria. The green dotted line from O1 corresponds to the solid blue line of the R10, and the dotted purple line of the O1 should be compared to the solid red line of the R10. As demonstrated by the 2 arrows, the differences between the accuracies of R1 and O1 is extremely small. Not only did the answers become more accurate with more training, they also got longer. For example, consider this math question about the number of oranges that I currently have. If I had asked it to DeepSeek R10 soon after we started the RL phase, it may have responded that the answer is 12, which is both wrong but also very short. It does not give us any insight into how the model came up with the answer. But as we run more RL training sequences that update the model weights, the answer to the same question may be the one shown in green, which is not only correct, but it also gives us an insight into how the model arrived at the answer. And that is exactly what we want from an LLM that solves reasoning problems. The supervised fine-tuning phase usually trains the model to be more verbose and more human-like in its answers, but DeepSeek showed that we did not need this SFT phase for correctness and for verbosity. Their model also started to self-learn things like reflection by revisiting intermediate steps, self-correction on the fly, and even becoming anthropomorphic as shown in this example from their paper. These are the attributes that RL training had previously endowed to AI models which played games such as chess and Go. And within a week of releasing DeepSeek R10, other researchers replicated the ability to eliminate the supervised fine-tuning phase, and it's always encouraging when others can replicate a conclusion independently and so quickly. However, all was not so rosy with R10. Notwithstanding the nice example we have here, R10 was often found to be too verbose, prone to mixing English and Chinese in its answers, and it provided unclear explanations even when the answers were correct. It was thinking correctly, but it was not expressing itself very well. And so they went back to a more traditional pipeline that they describe in their paper. And the R1 model lost the word zero from its name because it was in fact fine-tuned. But their training speed was still very fast. Now that could have been because of the DRPO algorithm, but people also found that their inference speed to prompts after the model was trained was also very fast. And the secret of that speed turns out to be the structure of DeepSeek v3. So to understand why R1 is so fast in training and so fast in inference, we have got to understand DeepSeek v3. Now I counted 5 clever features that gives DeepSeek v3 its speed, and we're going to go describe them right now. The first clever feature breaks the way that all previously deployed LLMs generate tokens. All LLMs up to December 2024 received an input prompt, processed it, and generated the first output token of the answer. A token is akin to a syllable or a small word. So the first output may be the word "an." It then takes the output token, appends it to the input prompt, and feeds it in again through the model, which then produces the second token in the output sequence, which could be the word LLM. Again, it appends the new output token to the previous prompt and generates the third prompt. This process continues until the last token is generated when the model outputs a special end token indicating it has finished responding. The number of times that a computer can run a model every second is the number of output tokens that is generated per second. And so folks have been using faster, more expensive computers so that they can get more tokens per second and therefore faster completed answers. Now around 2020, a clever team came up with a way to produce multiple output tokens every time that the model ran. It looked like this. Now a first run through such an improved model may generate 2 tokens as an output, for example, an LLM. It may then generate the tokens is a, followed by large lang, because a token is akin to a syllable. You can see that this would cut the time it takes to generate a full answer by a factor of 2. Not only would this make the inference 2 times faster, it would also speed up the training time, because every iteration of supervised or reinforcement learning training will have to run the model to get the expected answers. And although this idea has been around for years, its implementation added so much calculation to the model that it took the model almost twice the time to generate 2 tokens. In other words, there was no net gain. But in April 2024, a team from Meta and a French university devised a way to get multiple tokens generated without a big increase in the number of calculations. This is the main diagram from their paper. Incidentally, they also found that the process of generating multiple tokens per inference resulted in more accurate models. It was as if the model was being forced to think ahead a little bit more during the training phase, which kind of makes sense. Now, by the end of 2024, the DeepSeek team had implemented an even better version of this approach in their DeepSeek v3 model, which generated 2 tokens every time it ran. Now, in reality, the second token can sometimes be incorrect, and there is a way in both the Meta approach and the DeepSeek approach to identify and drop the bad second token. This does not happen very often, and we see an effective rate of about 1.8 tokens per inference over very long generation sequences, with little slowdown in the model speed. And given that this approach is now well understood in the AI community, I expect that other models are going to deploy this 2x acceleration very soon. Now, to understand the next 4 clever features in DeepSeek v3, we need to go one level lower into the structure of any language model. When an input prompt is ingested by the model, it is used as an input to a series of cascaded calculations, with one calculation feeding the next in a layered manner, which eventually results in the output tokens. The creators of LLMs expend much ingenuity into devising the type, the number, and the connectivity of these computational layers to give good model speed and also good accuracy. However, these compute layers have no knowledge of anything. The knowledge comes from the weights, which are billions and billions of individual numbers that are transformed during the training process from random gibberish to organized gibberish. These weights are then combined with the input prompt by the computational layers to produce a cogent statement. This simplified structure of LLMs reveals to us the 3 bottlenecks that slow down all models and add to their cost. First, we need chips like NPUs or GPUs to execute the computational layers. The more calculations a model needs, the more chips we must have, or the more time it takes us on fewer chips. This is called the computational bottleneck. We also must store the billions of weights in memory chips called DRAMs. The more weights means more DRAMs, which is our storage bottleneck. And finally, we need a very large pipeline to move the weights from the DRAMs to the compute chips. This is called the bandwidth bottleneck, and it is a brutal bottleneck because if the pipes are not wide enough to move the weights to the computational chips in time, then the compute engines will be idle waiting for the weights to arrive. That really slows down the model. And a higher bandwidth requires specialized DRAM chips like HBMs, as well as very fast electronic circuits in both the DRAM and the compute chips to let them transfer these billions of weights very quickly. And the second clever feature in DeepSeek v3 works to reduce all the 3 bottlenecks at once. The feature has to do with how computers represent common numbers. Most of us think computers can represent any value, but that is not true. Consider a bucket that only has 2 states. It can either be empty or it could be full of water. The empty state can be used to represent the value of 0, and the full one can be used to represent another value, like 1. Now, if we have 2 buckets, we've doubled the number of states to 4. When both of them are empty, that's a state. When both of them are full, that's another state. And when one of them is full and one of them is empty, that's 2 states. And these 4 states can represent 4 values, like 0, 1, 2, and 3. And every time we add a bucket, we double the number of states and therefore the unique values that we can represent. So with 3 buckets, we can represent 8 unique values. Now, computers store information in containers of electrons, similar to buckets of water, and we call these containers bits. And so you can think of 1 bit as equivalent to 1 bucket. The more bits a computer uses to store a number, the more value that it can represent. But the total number of bits limits the number of unique values that it can store. For example, if we use 32 bits to store a number, then we are limited to about 4.3 billion unique values. And the number of bits that we choose to store each of our numbers is called the precision of that number. Now, up to 2020, training used 32-bit precision to store the weights and the activations while it was doing computations. By the way, the word activation refers to the intermediate numbers that are calculated by the different computational blocks in the model and are passed around inside the model, like where the gray arrow is pointing right now. Since 2020, there has been an increasing usage of 16-bit precision for training, though some of the training calculations had to stay in 32 bits. And in 2024, hardware started to show up that would allow training with 8 bits of precision. But having just 8 bits of precision limited the number of values that can be represented to only 255 numbers. Training with that would require a lot of clever engineering. But that is exactly what DeepSeek seems to have done. by converting their weights from 16 bits to 8 bits, they relieve the storage bottleneck by reducing the size of the weights by a factor of 2. They also reduced the all-important bandwidth bottleneck because they only had to move half of the size of the 16-bit weights. And finally, they also reduced the computational bottleneck because a calculation on an 8-bit number requires much less time than an identical calculation on a 16-bit number. By reducing all three bottlenecks, their training and inference could have been accelerated by a factor of 2, an additional factor of 2. Now, to be clear, the use of low-precision numbers to improve speed and reduce storage has been applied since the mid-2010s to run inference of AI models on chips for cell phones, cars, and other efficiency-minded products. In that field, we even use 4-bit numbers for weights during inference. And we already are seeing the V3 model being distilled to 4-bit models that can run on edge devices. But DeepSeek is one of the early adopters of the new 8-bit hardware that is particularly suited for training, and it is plausible that they solved several hard technical problems and wrote specialized software to run their training chips and make this happen. Now, this is a very, very solid engineering feat, but also is one that I would expect to be soon emulated by every other LLM builder. After all, the 8-bit hardware for training is now widely available. Moving on to the third clever feature in V3. This one attacks the bandwidth and computational bottlenecks using a unique computational block inside the model. Today, almost all LLMs are composed of layers of this transformer block that was first invented in 2017. DeepSeek's V3 model stacks 61 of these, one on top of each other. Looking inside the transformer block reveals 4 other computational blocks. The 2 RMS blocks are tiny, don't impact the performance much. The feed-forward block does not use much computation, but needs to read massive amounts of weights from the DRAM. This is the place where the learned knowledge of the model merges with the prompt data and from where the next output token starts to take shape. Now, since 2022, researchers have already known that most of the weights that are read from the DRAM for this computational step end up not impacting the final result. So why are we reading them at all? Well, we're reading them because the exact group of weights that will impact the result depends on the value of the activation data that's coming into the block from the previous blocks. And that data depends on the input prompt and all the tokens that the model has previously generated. Now, we don't know these beforehand, and so we cannot select which of the weights should we fetch and not fetch. One solution to this is to divide the feed-forward block into subblocks that are called experts. Each expert would only read a portion of the overall weights, so that if we had 16 experts, each of them would only need to read 1/16 of the total weights. But the idea, of course, is not to read all the weights, and so a selection mechanism called the router is added to the block. The router looks at the input activation data coming in from the previous blocks and selects, using the content of the activation, a limited number of experts that will be used. How does the router know which experts will be used? Well, the router turns out to be a small AI model that is trained as part of the large model to identify which experts are best for what type of activation data. If the router selects 2 experts out of the 16s, then the bandwidth being read is going to be 2/16, which is an eighth of what we would usually read. This looks like a very good reduction in bandwidth. But while this mixture of experts method seems elegant in concept, it was not easy to train. And once trained, it did not perform very well versus dense models where we did not divide up the feed-forward block into experts. The DeepSeek team published their solution to this problem in January 2024, and it was a small 7 billion parameter model which they called DeepSeek MOE or DeepSeek Mo. They divided up the feed-forward network more finely. Instead of a traditional 16 experts, they used 64 smaller experts. This allowed each expert to train better for a smaller task. They then also realized that there are some shared tasks between the experts, and so they invented the idea of a shared expert, which is the green box in that last frame labeled 1. The shared expert is always turned on along with a few other experts that the router selects. Now, all this seems logical, which it is, but training MOEs so that each expert hones its skills is not very easy. And those experts have to run on different compute chips. And so the training algorithm had to not create bottlenecks where all the activated experts were physically located on the same chip. Again, there seems to be some very solid engineering here. And in the final DeepSeek v3 version, the overall model seems to have 671 billion parameters in its feed-forward blocks, and only 37 billion of these gets read due to the mixture of experts design. That's about a 95% reduction to the DRAM bandwidth bottleneck, and it's extremely impressive. Now, of course, every time the model runs, a different group of 37 billion weights are read, depending on what the router sees in the incoming activation. As a comparison, it is speculated that GPT-4, which also uses mixture of experts, has about 1.76 trillion parameters, but we don't know how they are split between the different experts. Now onwards to the fourth feature of DeepSeek, which also addresses the mighty bandwidth bottleneck. We have to go back to the basic transformer block and now look at the attention block, which performs the clever task of extracting the relationship between the many words in the input prompt. This block reads a large amount of activation data from the previous stages and is the place where a lot of computation occurs. Now, unfortunately, the number of computations here increase quadratically with the prompt length. This is a massive problem during inference because we want the reasoning model to generate long, clear answers. And as the model generates more tokens, the prompt of the next iteration of the model is going to get longer, which means that the number of computations to generate the next token is also going to be increasing all the time. Not only that, it's going to be increasing quadratically, which makes things much worse. So, the model takes longer and longer to generate the next token. Now, luckily for us, a team in Google in 2022 noticed that a new prompt is made up of the old prompt plus the token that was just generated. That meant that a lot of the computations had to get repeated every time the model ran. So to speed things up, they stored the outcome of previous computations in the DRAM, and when the model reran with an updated prompt, they just had to read the results of the old calculations from the DRAM and only do the calculations for the new tokens. They called this idea the KV cache, and that thing is used everywhere. So the KV cache is a super smart idea, but it converts our computational bottleneck into a bandwidth bottleneck. That was not a huge problem when the prompt size was small. But as we increase the prompt size either overtly by adding large documents into the prompt or covertly when the service provider adds invisible preambles to the prompt, the bandwidth taken to write and then read back the KV cache to the DRAM can become comparable to the bandwidth of the weights themselves, especially because we've just reduced the weights significantly by using mixture of experts and low precision numbers. When the DeepSeek team published their paper describing their V2 model in June 2024, they described how they looked at the data that would be stored in the DRAM as KV cache, which is the shaded part of this diagram, and they postulated that there is a lot of shared information between the different stripes of data. If there was shared or repeated information, then the information can be compressed into a smaller amount of data that is free from repetition. It would cost a little bit of compute to do this compression, but it can be worth it if the DRAM bandwidth is reduced. And that is exactly what they did. Instead of storing all the stripes of the blue data into the DRAM, they used a well-known compression technique called low-rank adaptation to compress the blue stripes 10 times smaller and then store the result in the DRAM as their KV cache. When they needed this data to process the next prompt, they just decompressed it back to the original blue stripes of the data. The amazing thing about this process is that by creating a relationship between the stripes of blue data through the low-rank adaptation, they found that the model actually got more accurate because there was more communication and coupling through compression between the data streams in the model. This story rhymes with how multi-token generation caused an increase in accuracy by bringing the data of future tokens earlier into the computation. Now, the fifth clever feature of DeepSeek v3 has nothing to do with the model itself. It's about the efficient use of hardware through some shrewd system and software engineering. Much of it is described in this paper on their Fireflyer training system from August 2024. There are some more details sprinkled in follow-on papers, all of which can be summarized in 5 main points. First is that they were the first to publicly announce the use of low-precision training. They developed lots of clever quantization algorithms to deal with very limited number of values and worked around many issues in the first generation of 8-bit training hardware. Second is that they built their own in-house communication and data movement library, which they called HFReduce. It used the GPU's resources more frugally. They also used the CPUs to do updates to the weights as the data moved between the chips during training. This also preserved the GPU resources for training. Third is that they developed their own in-house scheduling software to make sure that the data fetching from the DRAMs is happening at the same time that the computations are happening on the compute chips. Their goal was to keep the compute units running all the time rather than have them being idle waiting for data to arrive from the DRAMs. Fourth is that wherever the open source code was not fast enough for their needs, they went ahead and wrote their own efficient code. And finally, they really relied on the clever algorithm designers to ensure that the training and inference will lighten the load on the system through mixture of experts, multi-token generation, MLA, and the like. And so far, this seems to have worked very well. So as I was quickly slapping together this video over our weekend, 2 thoughts kept on occurring to me. First is that the DeepSeek team must have access to a ton of 10x developers and some super insightful managers that are able to coordinate and harness that powerful mass of gray cells. This is so clear not only from the 5 features that they used to accelerate DeepSeek v3, but also in the pace of innovation that they've been putting out there over the past year and how pragmatically they used open source code except when custom development gave them a real edge. If you're not familiar with the concept of the 10x developer, there is a video on the topic in our Semi-Learned YouTube channel, and there's a link to that in the description box below. The second thought I kept having is that I saw this movie in the AI theater 10 years ago. In 2012, AlexNet launched the wide adoption of convolutional deep learning and made the practical use of AI a reality. 3 years later, in 2015, we got VGG, which was a natural scaling upward of the same concepts that were explored in AlexNet. It created a panicked rush to add more and more computational power to AI chips. But then in 2017, Google published the MobileNet paper showing that the depthwise convolution could solve the problem more efficiently. It's not that we did not need more computational power after MobileNets arrived, but there was more balance and an emphasis on developing more clever algorithms for using the hardware more efficiently. Now, for LLMs, we had gotten GPT-1 in 2017, and ever since, the natural scaling approach seems to have had the ascendancy. And I'm thinking that the recent exploits of DeepSeek will usher a more balanced approach between efficiency and brute force scaling. Now, finally, I wanted to cover distillation of DeepSeek models into smaller ones that could run on edge devices, but I ran out of time, so it's going to have to be for a future video. And so that is it, folks. Thank you so much, and best wishes to you.